Hi guys, in our last video we caught a glimpse at the graphs of the parent exponential functions, and that is to say that we kind of looked a little bit at their shapes and how they behave in a table, but specifically about what we could say about y equals b to the x, this most basic parent function. So what I'd like to do in this video is just kind of introduce the values of a, h, and k. And as we've looked at transformations in the past, we've seen how these values affect the graph of a parent function. And so the neat thing about the graph of y equals b to the x is that it is affected in the same way as other functions by the values of a, h, and k. And so with respect to what a, h, and k do, let's kind of review what we know about these. It says that h is responsible for our horizontal shift of the function. And what I write looks dishonest here. I mean to say that look, our h value is inside parentheses with our x, but that there's a minus in front of it. And so whatever h is, it tends to look backwards from what it really is, whereas k is responsible for our vertical shift. So when we talk about vertical shift, k is our sole shifter, and it looks honest. So it having a positive in front of it in this formula here means that it's going to look like what it actually does there. Now I write here, if there's a negative in front of the independent variable x, that means that if you have a negative planted right up here in front of your x, we say then the parent function is reflected about the y-axis. And a perfect example of this would just be when we looked at the parent functions basically in the last video. If you have a negative in front of your x, it's going to be a y-axis reflection of our original parent function. Now, if there's a negative in front of our a value, now that is a negative out in front here, then we're going to say that the parent function is reflected over the x-axis. So what I'd like to do essentially is be able to very, very quickly sketch graphs of exponential functions like g of x and h of x that you see here, where we've got some exponential function where it kind of is manifested with other values here like h and k. So it says for each of the following, graph the parent function y equals, this should say, base to the x power on the coordinate plane, and then graph the transform function. Be sure to sketch in the horizontal asymptote and label it. So here's what we're going to do. We're going to graph our parent function first, and then we're going to work on the transformations. So when it comes to graphing the parent function, here are some things that I would say that you would want to be able to fire out very, very quickly. And that is that there has to be a horizontal asymptote on the x-axis. And so very first thing is our parent function, we'll go ahead and put its asymptote on there. We'll say that it's at y equals 0. So what point should I plug into my parent function? Well, we know that these graphs are really just kind of these growth or decay curves, but they're only really interesting in and around the origin. So we're going to plug in x values that are more central in the coordinate plane. And what we see is this. We get 3 to the 0, which is 1. 3 to the negative 1, which is 1 over 3. And 3 to the positive 1, which is 3. So with respect to our parent function, shoot, you guys, I suppose we could say it goes through 0, 1, 1, 3, and negative 1, comma, its reciprocal. So here's our always increasing parent growth function. And we're going to label this f of x. Now our job is to be able to graph these transformations, g of x and h of x, a little bit more quickly. And the thing here is, as long as I know what this parent function looks like, and I know what kind of transformations I would expect to see here, then we can graph the transformations rather quickly. So first things first, when I look at this 2 here, I say, well, what is this? I look at this as a horizontal shift. This is an h value here. So a horizontal shift, and we're going to say it actually goes left 2 units because our h value looks backwards. So what that means is, if I wanted to sketch this, all I would need to do is graph my parent function first, and then we're just going to pick up all the values that we had on our initial graph, and we're going to bump them left 2. As far as would that shift the horizontal asymptote here, the thing is, we didn't shift it up or down. And so h is going to shift our asymptote left and right, and because it's a horizontal asymptote, it really doesn't matter. So our horizontal asymptote is going to remain at a height of y equals 0 in that case, and this would be our new exponential function, g of x equals 3 to the x plus 2. So I'm going to label this g of x. Now when you look at h of x, this is a little bit different, h of x. You'll notice that we have not an h value, but this is a loose constant. And so this is our k value. So I'm going to refer to this as a vertical shift up 2 units. And so the same thing here. If anybody asked me to graph this, I wouldn't graph this first. I would graph the parent function first, just 3 to the power of x. And then what I would do is just go shift it. So because I know everybody shifts down twice, I'm going to grab this 0, 1 and shift it down twice. I'm going to grab this point here and shift it down twice. And I'm going to grab negative 1, comma, suppose this was at 1/3, and shift it down twice. And that would put it about right here. So the big question is, should I shift the asymptote? Well, you know, the asymptote always shifts. It's just that you don't see it shift when it shifts left and right, but you do see it shift when it shifts up and down. So we're going to label this y equals -2, and we would get this graph right here. Okay, it would actually overtake it right in there. And we'll call this one h of x. So you can see how graphing transformations is made really a lot simpler if you know what the graph of the parent function looks like, okay? So one thing I want to comment on before we kind of look at maybe graphing a few more transformations and being done with graphing transformations is just that when we shift these exponential graphs up and down, that's what causes our asymptote to appear to shift here. And so I want you to notice something here, that y equals -2 is the height of our asymptote, but generally speaking, the parent function always has its asymptote at a height of 0. So whatever our k value is, that's actually going to represent the or the horizontal asymptote of these graphs here. And so I suppose that when we look at, let's see, I've got to scroll up here. This slide right here. One thing that we're going to want to add to our list right here is that our horizontal asymptote is always at y equals k, whatever our vertical shift is going to be. So let's look at putting together a few more shifts here. Again, you know, I have this parent function y equals 3 to the x, so we're going to be using the same parent function. I know I built a table on this last one, and so I'm going to borrow a little bit from it. If we were to plug in -1, 0, and 1, and we say let's go take 3 to the 0, or 3 to the 1, or 3 to the -1, we get these same central values again. Except for this time, I'm going to use a little bit different transformations. And so here's our, whoa, try not to make this part of your graph look like that, but I'm going to go ahead and go with it here. F of x. If we wanted to graph, say, a transformation like this right here, what you notice this time is that it is a series of transformations. And so I noticed that this would go right 1 and up 3. That just means we're going to switch our color here, grab every point, go right 1, up 3. So this would, 0, 1 would shift here. Right 1, up 3 here would shift to there. And from -1, 1/3, right 1 and up 3 would put it about right here. And we would also have to say, well, my k value is 3. My asymptote's also going to be at a height of 3 here. And so we're going to label this y equals 3. We're going to draw pretty much, it looks like we're on the asymptote, even though we know we're not. And then have this grow over time. So here's our first transformation. We'll call this one g of x. Now our last two transformations, you're going to notice that I put in some negatives here. And this is just really representative, of course, of reflections. So the question is, what kind of a reflection would I expect to see? 3 to the -x. Since the negative is in front of our x value here, then I know that I can really just take my original parent function and make all the x values their opposites, okay? And so where would my new points be? Well, from the parent function, if I had these tabled values here, let's just even say if I did make all my x values their opposite, this would be +1, 0, and -1, and our y values would have stayed the same. Now you don't need to table this, but I do want you to see that instead of being at -1, -1/3, if we reflect over the y-axis, we're going to be at -1, 3. We're going to be up here. And 0, 1, you know, if you put a negative in front of 0, it's still 0. It's still at 0, 1, but -1, 3, 1, 1/3 would be this point here now, and this was formerly this point that you saw on the left side. It popped over the y-axis there. And so if you see a negative in front of your x value like this, it's going to look like your parent function is just going to flip over the y-axis, whereas if we now go back and we say, looking at this last one, and I should have labeled this is h of x here. If we take our original parent function, we have a negative in front of our base value here. It doesn't mean our base is negative. This is the same thing as j of x equals -1 times 3 to the x. So the negative's out in front. But this would mean all of our original y values would become their opposites. So instead of -1, +1/3, we'd be at -1, -1/3. You can see that that flipped over the x-axis. Instead of 0, 1, we're at 0, -1. Instead of 1, 3, we'd be at 1, -3. You would see that this still represents growth, but it does so in a negative direction here, and we'll call this one j of x. So going forward, we're going to be sketching transformations, and it's important that you know what your basic parent functions look like, because then we can just transform those. Cheers.